Okay, welcome back to working through problems exercises together. There are 28 problems in chapter 3. So I'm going to do random number between 1 and 28 and get 19. So let's go find problem 19 and see what it looks like. Norm of a sum. Use the formulas 3.1 and 3.6 to show the following. A is orthogonal to b if and only if the norm of a plus b is equal to the square root. And then non-zero vectors make an acute angle if and only if norm is greater than this value, and make an obtuse angle if and only if it's less than. Okay. So let's go look at these. Let's go look at these equations and see what they are, if they seem like they're going to come in handy. Okay, so 3.6, and it says first equality comes from 3.1. Okay, well 3.1, this is just, this is our norm of a sum term, right? Which just comes from doing the inner product of the sum and then taking the square root. So that's fine. And then where did 3.6 go? It's over here somewhere. Sorry. Here. Okay. And this one is taking that and then inserting in the definition for an angle for the 2x transpose y. So we get this here instead of the 2x transpose y. Okay. All right. Now let's go back and look at our number. Our question again. Okay, this one is saying A and B are orthogonal if and only if the norm of these is equal to A plus B squared. So, okay, fine. So we're saying A is orthogonal to B if and only if the norm of the sum is equal to the square root of the norm of A plus the norm of B, right? Which, sorry, let me get back to here. Okay. Oh, squared, right. Okay. Which seems relatively straightforward, I think, because we said one of our things that we said was that if two things are orthogonal, then that means that their inner product is 0, right? The inner product of A and B is 0. So just using that formula from before, it's fairly easy, I think, to say the norm of A plus B is equal to, here, let me draw a line under this just to like start over here. If A is orthogonal to B, A transpose B equals 0, and the norm here has got to be equal to the square root of the norm of A squared plus 2A transpose B plus the norm of B squared, right? And this term right here, we said if they're orthogonal, that has to be 0. So we've proven, the thing that we were asked. Well, so technically it says we have to go if and only if. So that means going both directions. We showed if they're orthogonal, then the norm is equal to the square root of the sum of the norms. We have to go the other way too and say, given that the norm of this thing is true, can we prove that it's orthogonal? And really, I think that we can because given if it's true, then this part here has to be 0, right? there's no other way for that term to go anywhere. There's no other, it's not like there's anything else that could add or cancel out of the norm of this formula. So, you know, if you came across the norm and were able to show that it was equal to this, then you would know it was orthogonal. Okay, so that's part A. And then for part B and part C, these two I think should probably go together. Make an acute angle if and only if it is greater than this value here, this square root of the squared norms, and obtuse if and only if it is less. And so for that, I think we are going to need this 3.6. Let me see if I can get it to go back there. We're going to want to just insert in, for the 2x plus y, we're going to want to insert in the norms times the cosine of theta. So let's, whoops, wrong one. Let's do that. So, so we're going to do essentially the same thing here, except, you know, we're going to say norm of a plus b is equal to the square root of norm of a squared plus, and now here we're going to put in the formula. So we're going to say, you know, 2 norm of a, norm of b cosine theta plus norm of b squared, right? Let me double check that I got that, that we got that right. We just want to double check, make sure we don't mess anything up here. So the only difference between mine here is that this one has this, you know, it's the squared norm on the left-hand side, whereas I have the square root. I have the square root there. Whoops, whoa, come back. Yes. Okay, and then, okay, so now all that's really left is to think about this cosine theta here and what that means for acute and obtuse angles. So, so we just said, you know, we just said if it's a 90 degree angle, if it's orthogonal, then this whole term is 0. And of course that makes sense for this part also. So this whole chunk, 2 times norm of a, norm of b, the norm of anything is always positive or non-negative. These are either 0 or positive. And so the only thing that sort of changes there is this cosine of theta. And okay, so what does the cosine of theta do? Well, remember, it's the x component of the angle as you sort of travel around the unit circle here, like this, right? So when your angle is 90 degrees, the x component of that vector is 0. So cosine theta is 0, and this whole term is 0, which is what we just did in part A. For an acute angle is one where it's less than 90 degrees, which means it's over here somewhere, right? And in that case, its x component is going to be greater than 0, right? So that would be greater than 0 if it's acute. If theta is acute, which you could also say if theta is less than 90 degrees or less than 2 pi, pi over 2, however you want to think about that. And then if it's greater, then that means it's over here somewhere, right? Which sure enough means that the cosine is negative, which means that cosine of theta has to be less than 0, and which means this whole thing would be less than 0. So this whole thing is going to be, this whole term here is going to be greater than 0 if the angle is acute, less than 0 if it's not, which means that the overall norm will be greater than just the norm of the two sums if it's an acute angle, and less if it's an obtuse angle. And I'm not sure, does it ask us to draw a picture of this or not? I don't remember here, but wait, where is it? Yeah, draw a picture illustrating each case in 2D? Well, we kind of did that. The only thing I would say then, just to sort of like add on to this idea, is that right, so if you have two vectors who are at right angles to each other, like this, right, then when you add them together, right, let's say this is A and this is the B vector. When you add them together, you put the B on top of the A, dot, 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 you go out to here somewhere, and you get this vector here. This is our A plus B, right? And now, this is just Pythagorean theorem. The length of A plus B is surely going to be norm of A plus norm of B. A squared plus B squared equals C squared, right? And if they are less than 90 degrees, so this is the right angle, this is the orthogonal. If they're less than 90 degrees, that means we have A out here somewhere, B is over here somewhere, right? And we are adding A to B, so that means A plus B is going to be over here somewhere, right? And if you think about, like, okay, the norm of that, the length of that thing, which is actually this vector here. I actually need to move all this stuff over because this is this vector. I lost some bars. That's okay. Okay, so it's that long thing, right? And that is clearly longer than the right angle case, right? You can imagine, like, here's my right angle triangle, and as I tilt this guy this way, then it goes sort of, this thing gets longer, right? And conversely, if I tilted B the other way, so it's obtuse, here's A, here's B, right? Then when I add A plus B, I'm going to have to go this, I'm going to have to add B to the tip of A over here. So my A plus B looks like this, right? This is B. Then it gets shorter, right? So here's the acute, and here's the obtuse. It's tilting in. So, you know, it's just a nice, like, it makes sense intuitively that the length of this hypotenuse of this triangle gets longer as this angle is acute and shorter as it's obtuse. Okay.